so that they kind of know what they're asking. Okay, so I'm also currently recording, and I'm going to talk to the online people. Sorry if you can't see me, I got out of the screen because I'm mostly going to be talking to them. And I'm sorry about the picture being weird, but I can't do anything about that. So we decided our 3 topics. We're going to talk about our back reviewing the scientists and what they did, redox reactions, and organic naming. So let's talk through all our scientists. Okay, the big ones you need to know are going to be Dalton, Rutherford, Thompson, Avogadro. I'm not 100% sure how to spell his name. And Bohr. They're not going to test you on spelling. I can promise that. Not much better. Okay, so Dalton's typically called the first one. He's the one who did the, yes?
Wasn't he like the 1700s before
I do not know what his number, like when he started. Oh, she's bringing her stuff back. But he came up with the first set of theories. And so his theories are things that if they were to ask you about his theories, they'd want you to think about like when in the process did they come up with different things. So you might recognize what these guys came up with couldn't have been in his theories. So like if they said Dalton's the one of his postulates or his idea of a theory that atoms are made out of protons. We know that can't be true. You're welcome. Did you have any questions about your lab?
No, I'm good.
You're good? Have fun.
Yes.
I hope it goes well.
Okay, me too.
made of just protons?
Or like for Dalton's time, they wouldn't have thought it's possible for atoms to be any smaller. They would have no idea of that. So Dalton said things like atoms are the smallest piece. He also thought all atoms were identical. All atoms of the same element. Sorry. All atoms of same element are identical. And we've since learned that's not true. Why is that not true? We have isotopes. Isotopes are all different masses, but they can still be the same element. Another thing that he is the one that came up with the idea that atoms could be rearranged to create new compounds. And that is still true today. In this book here, page 64, talks about the history of the atom. I was going to see if it had any good questions for us to go with, because it's just a good place for practice. And no. Oh, look, I did spell Avogadro wrong. So I spelled Thompson wrong, but zoomed all your book guy, he's the one who doesn't put a P in it, but then other places do. So I'm not sure whether it's supposed to be or not, but and they didn't put Bohr on here, and Bohr is kind of questionable. He's one that chemists kind of talk about a lot, but his theories are kind of weak. So those would be the 3 big ones that I would have you guys look at, and they didn't give us any good questions. So let's talk about Rutherford. Do you guys remember what he did? He did gold foil. So being comfortable with each of their experiments is always a good idea. Do you remember what the gold foil experiment was?
That's the plum pudding, right?
Plum pudding discovered the electrons.
That was, wasn't it like if it could go through or something?
Yeah, he's the one who came up with the concept of he didn't name it protons, but the protons there in the center of the nucleus. I didn't go in order. Maybe I should have. Do you guys want to go in order?
Wasn't it like a filtration kind of deal?
Let's take a step back. Let's go in order. Filtration could be a way of thinking about it.
Like, that's not what it was about, but
So Thomson came first because Thomson's the one that said electrons are present. He found the idea that electrons are there, and that was a revolutionary idea because before they always thought atoms were the smallest and they couldn't be broken down. Now they realized that they could be broken down. And so he did the cathode ray tube, often referred to as CRT, cathode ray tube experiment. And that's the one that's kind of like neon light. And so you should forgive my drawing because I'm not talented at that and you guys know it. But like this is going to have a light beam inside here. Yeah. And so it's filled with a gas. One of the noble gases is a great one to use, but any gas could go in there. And then they electrify it and they send electricity in here and they realize that that caused your gases to break apart. And so that's where you got this beam of light. And Thomson, I realized that had to be the atom and there had to be things in the atom coming apart. So that's when he used a magnet that had those opposite poles. And so when that happened, it caused, if you put the positive one there, it caused this light to bend down towards that. And when we put the negative, it bent away. And so he was able to deduce that those must be negatively charged particles inside your atom. And of course, if there's negatively charged particles in your atom, there has to be positively charged particles. So, but he didn't know how that worked. And that's where the plum pudding came into play. And so he came up with the model of the plum pudding, which we don't ever eat anymore. So I say chocolate chip cookie because that's something we do eat. And he thought that the positive was more of like a gel that kind of flowed all over. And then there were just these like electrons that were placed throughout, like the chocolate chips would be throughout a cookie, or the plums would be throughout a pudding. And so the cathode ray tube helped us to identify electrons. So he had to create a new model, which then allowed him to come up with plum pudding. Rutherford said, since this was just a theory, or probably not even necessarily a theory, Rutherford came along and he wanted to prove this to be true. So he came up with the idea of the gold foil. And so he is the one who came along next. Do you guys have questions about him? Or I'm going to switch to Rutherford. Okay, so what Rutherford said in his gold foil is he put this giant deflecting screen back here on a piece of gold foil, just like aluminum foil, but made out of gold. So it had all these gold atoms inside it. And the nice thing about gold is it's a pretty big size atom. So there's going to be some good size holes in it. And so what he figured is that this positive gel would even the positive charge out. So it would be kind of a weak positive charge. And he was going to shoot positive particles through here, and they should be able to just pass right through. If that happened, then the plum pudding model would be correct. Obviously, it wasn't correct because we know now that's not what happened. And in fact, what was going on is these pieces were shooting all sorts of ways. And that means that the positive charged gel couldn't be just evenly dispersed. It was in very tight, specific areas. And those specific areas he identified as being the nucleus. And so he said positives are in the nucleus and negatives are on the outside, but even he knew obviously that can't be the case because they'd be attracted to each other, and so there has to be something more going on. But that was once again a new revolutionary idea.
so they didn't know what the nucleus was before Rutherford?
Correct. Rutherford's the one who came up with that concept.
See, I thought Thomson knew what it was, and he was putting electrons in the nucleus.
Mm-mm. No, he was not.
Did Rutherford have a
So he didn't necessarily call them protons. He said that they were the positively charged pieces that were in the center, and they're what we now call our protons. So he's the one who came up with that idea first. He's credited for that. like like Thompson, I know called them corpuscles. I don't remember if Rutherford called them protons or not, but that's kind of that. So those would be 3. Dalton's the same one who did Dalton's partial pressures. So when we talk about partial pressures and the idea that several gases can be added together, it's kind of a side thing, but I don't know that that would ever come up, but for whatever it's worth, because a lot of his experiments were done using gases, and that was kind of the first idea of chemistry evolved from how they realized gases were there and how it worked. And so that's how that happened. And then Avogadro, I would just say for you to know about, he, obviously he's the one who discovered the mole and created Avogadro's number. So he came up with the idea of the mole. And we know how important that is because that's how we're able to compare all of our atoms together. Even though they have different masses, they're all based on the same number. So it makes life easier. And that number is times 6.02 times 10 to the 23rd. That's Avogadro's
Third, I
number.
was talking about last hour. We were talking about charges and the K values.
Oh, in physics?
Yeah, and we also learned the,
9 times 10 to the 9,
The-
the constant.
The constant of Coulomb's law.
it's like the force between 2. But we learned like the.
And so he asked us what the charge was, and I was like 9 times 10 to the 23rd. And I was
So then
thinking,
we're like, you're looking
You combined your chemistry and your physics. Nice. Okay, those would be the major scientists to know. Bohr, we started to talk about, he's the one who came up with an idea of the electrons being tied in shells. But even since then, that's been discredited. So we've kind of not talked about Bohr as much. And you guys know that we know that there are things smaller than protons and neutrons and electrons, or protons and neutrons at least, right? And there are things like quarks. Cool. I'm going to erase this. Awesome. Then next up on our list would be redox. I know that sounds really fun. The scientist questions in the AP test, I have seen them have a question here or there about it. Not every test always has them. So it's not something I would say you should spend all of your time studying, but it is worth kind of reminding yourself because every question you get is a good question. Okay, class, we're going to skip to not classifying reactions, but redox reactions. It is on page 94 in the 5 Steps to 5 book. '94. Hey Dylan, I'm
Okay.
so glad you came back.
Yeah, I just like your
Have
Thank
fun.
you.
Okay, so we're gonna redo redox reactions. Do you have any problem with me just going through this example they have here in the book? Is that fine? Okay, so we're gonna do this example, Cr2O7, 2 minus plus Cl minus. That's what we're doing. Yep. That makes Cr plus 2 and Cl. Okay, so a couple things I want to say before we get started on redox. Remember that this is kind of a nice equation because first of all, it's written out in its chemical formula. So you don't have to remember that this is dichromate, but you cannot guarantee on the AP test that they're going to give you the equation. Sometimes they do, sometimes you have to write it. So you have to know your polyatomic ions. The other thing you have to know, you have to remember that our chromate becomes the Cr plus 2. Chromate and the other one, permanganate. Chromate and permanganate were the ones I had you memorize on your things you're supposed to know but don't know sheet.
What is it?
So dichromate and permanganate were ones I had you memorize, but remember this sheet, and this is a really important sheet to take back and study and review. Keep it by your bed, look at it every night. There's a lot of polyatomic ions, and the more you know, the better your life's going to be. So then that's important. Another thing to typically remember is if you had to guess If it's got chromium, it's got manganese, most of the time what's going to happen is all those oxygens are going to leave, and then it's going to turn into its chromium ion. Okay, so we're going to start with that. So the first thing we want to do is separate it into the two half equations. So dichromate becomes the chromium
Isn't
ion.
Cr plus 3?
It can be sometimes, but in this instance, it's +2. Just kidding.
It says plus
Just
2.
kidding. Jokes.
Because
Just
I
joking
was
with you.
looking at
I'm
this
just
sheet.
joking with you. Permanganate becomes +2. I apologize. My bad. Chromate becomes +3. Permanganate becomes +2.
That would.
My bad. Thank you, guys. Okay, so we've got basically two half reactions happening, and that's the best way to do your redox reactions because you're most likely to get them right that way.
Will they tell you if it's a redox reaction? Like, will they say that dichromate reacts with a chlorine ion, and then you'll just have to like, so you're just gonna have to recognize that it's a redox.
Yes, I have seen in the practice test and the one they did this year, more often than not, they give you the equations and you haven't necessarily had to come up with the products, but I can't guarantee that because in the past they had. And a lot of times I've seen them just have you balance it once the equation's written. But I want you to be prepared in case. So balancing it becomes really important. So the very first thing you need to do is make sure that your basic equation is balanced out correctly. Like, for example, we've got 2 chromiums on the left, but only 1 on the right. So I'm going to go ahead and put a 2 there, and I know I need to start with 2 chlorine ions and then go to chlorine. That's diatomic chlorine. I may not go in the exact same order as this, but so far we've agreed. Then a couple things we want to look at. Bless you. The book does electrons second. I like to do electrons first. And so I'm going to go ahead and put those in. And if we look at the fact that chromium on this side is a +3, but on the left side, what would be chromium's oxidation state? Good. So we've got -2 on our each oxygen, and there's 7 of them, so it's -14. Overall, I need to have a -2 charge, so this side has to be a +2, which puts chromium at a +6. And I have 2 chromiums becoming 2 chromiums. So if I'm transferring 3 electrons each time on this side, and I'm doing that how many times? So I'm going to multiply that by 2. So I've got 6 electrons total transferring on this half reaction. What do we have happening on this side? You go from -1 electron to 0, because remember it's atomic, and it's the standard state, it has no charge. So then I had a loss of 1 electron being transferred. And there's 2 of them that are happening, so overall I've got 2 electrons transferring.
Does it matter which side the coefficient's on?
What do you mean?
So on, for the dichromate, the coefficient's on the product side, it's C and it's on the.
Right. So I had to do that just to balance it specifically.
Yeah, I know, but
You
when you
know?
go to multiply, it doesn't matter.
No, because it's still the same number. I'm just looking at how many total chlorines were changed. So I had the 2 in front to make it equal on this side, but I had 2 chlorines that are being reduced or oxidized in that instance because it's losing an electron. So far, so good. Okay, so they obviously don't match. Can't gain 6 here and only lose 3 here. So I'm going to need to change this so that this becomes 6 electrons. So I'm going to need to multiply everything by 3. So instead of having 2 chlorines, I'm going to have 6 chlorines and then 3 chlorine diatomic atoms. And then before I squish them back together, I want to make sure that all my atoms are balanced correctly. The reason I like to do the electrons first is because if I needed to change that number of oxygens, it would have messed up my total number of oxygens. So that's why I do electrons before it, but this book did it the other way. So we need to see the fact that I've got 7 oxygens on the left, but no oxygens on the right. Probably not okay. So I'm going to rewrite it down here because I didn't give myself enough room. And since these are all aqueous solutions, I know that I have water available, and I know water has oxygen in it. So I'm going to add some water molecules because they come with oxygen. So I need to add enough water molecules to balance out my oxygen. So that gives me 7 water molecules. And of course,
And then don't you have to add the H to the other side?
can't just add H's without balancing those out. So then on this side, I'm going to add 14 H pluses. And that's fine because most of the time these redox reactions are done in acidic solutions. But if you were given some information and it said this is done in an acidic solution or in a solution with this much dilute sulfuric acid or something, that's just their way of telling you that it's an acidic reaction. It is not telling you to put sulfate in here as your ions anywhere. Okay? So then the last step would be to squish it together. And sometimes you'll have H's on both sides and sometimes you'll have waters on both sides and you'll want to go through and balance those out. But we don't. So I'm just going to copy it all down. 14H plus Cr2O7 minus 2 plus 6 Cl minus 2 Cr plus 3 plus 7 waters and 3 chlorine atoms. Molecules. Just kidding. If you're ever stuck and you're wondering, is my equation balanced correctly? If you can't tell, you should always also have a balance of your charges. And that's true of all things. When we've been working on our acid-base reactions, it's also a good thing to check to make sure you moved your hydrogen or whatever correctly. And so like we've got 14 positives. Here I've got 1 negative, or pardon me, 2 negatives. And then I've got 6 negatives. So it looks, I put the negative on the wrong side there. But so 14 minus 8 is going to get me a positive 6 on my reactant side. And I've got 2 plus 3, so that's plus 6. And water and chlorine have no charge, so basically plus 0 and plus 0. So that means that I have plus 6 on this side. Most of the time, if you can get your charges to balance out like that, then you correctly balanced your equation. And it's always a good moment to make sure that you have the right number of atoms to be balanced as well. Because if your electrons balance, your atoms should balance, and life will be good. That's an example of how to do a redox reaction, and I would jump into organic unless you guys have a question.
So like what kind of questions would this be on, like a multiple choice asking us to just write through that reaction?
Well, in a multiple choice type question, I would see them ask how many total electrons are transferred. So then you would say 6, because that, don't add them together. Remember, 6 were gained here, 6 were lost here. So overall, that's still just 6 being traded. And that would be a great question. Maybe identifying which one was reduction, which one was oxidation. That's the type of question you'd see in a multiple choice setting, where they might give you an equation and you have to answer questions about it.
Okay, so the chromate was reduced and the chlorine was oxidized.
Right, and we know that because chromium went from a plus 6 to a plus 3, so it gained electrons because it became less positive. And so that would make it reduction because we did that silly GR, Leo goes GR. So this is reduction. And then this side we went from a -1 to no charge, so that would be oxidation. Or Leo, losing electrons is oxidation. Then in an FRQ is where I have seen them have you balance it the most. They could give you a lab setup where you're doing a redox titration. And they give you the experiment and say, these are your reactants, worst case scenario, and you have to come up with your products. But I would bet they'll give you the equation, and then your job is to balance it and then be able to answer questions about what's happening in the redox titration. So dichromate would come with a color, and as the reaction ran, it would change to a different color. Switch.
So if we titrate with chlorine on them?
So that would be one option. Yep. there's other things that can be titrated with. Any halogen would be able to work here. And so then you would do the same kinds of things we'd be doing with our titration calculations. Fair enough? Okay, you're going to talk about some organic naming and then we can be done. Okay, so I don't know if this has any good organic practice. I think it would have it at the end. Nope. Sorry, guys. I'll just come up with stuff. So I will say on the AP test, in the past, they've always said there would be no more than 3 questions or 3 points on the test devoted to organic. And then they've said for these tests that they are going to even decrease that further. So organic won't be something that's necessarily tested on. What I found on last year's test was while it wasn't actually a question they asked, almost all of the compounds they gave you were organic compounds. So people that didn't have any experience with what organic was, and they said something like butanes reacting with cis-2-trans butanol, they were totally freaked out because they didn't have any idea what that was talking about. But when you saw the molecules and you had a little background on what organic is, even though those things like cis or trans you didn't know about, you kind of felt comfortable doing with it. Does that make sense? So mostly I just want you to have some comfort with organic. So that whatever questions they throw at you, you're like, okay, I can trust them. That's a compound, and then go for it. Does that make sense? So remember, your organic ones are going to be like these giant chains of carbon. And on your carbon, you're going to have different things like functional groups. And carbon always is going to have 4 bonds. So you might have double bonds or triple bonds in places. So when I drew this molecule, I set up some carbons in the center. I just kind of made up some double bonds in there to try things. I don't even know if this is a real compound out in the world, but I made it up. We have these 2 extra groups attached, and we'll talk about what they are. And then I went through and put hydrogens all over the place just to make sure.
Is that right, having a double bond with that?
Mm.
Yeah, because I don't think. And so it'd be
Actually,
C.
let's get rid of. So
I
1,
already
2,
wrote
3.
that H.
Well, there you go. Put it back. 1, 2, 3, 4.
No, I didn't.
Can scribble through it.
So carbon can only have 4 bonds.
Correct.
It has 4 electrons.
Correct. It has 4 valence electrons. And so in order to be at the lowest energy level would be to gain 4 more electrons so that it's got a filled s and p orbitals. And so something like this, when you're going to name your organic compounds, you start with identifying how many carbons you have. Because the number of carbons dictates that prefix. And this has 4. Whoa, 5. Sorry, I can't count. Just stopped on my 4th one for no good reason. So 5. And what is prefix to that? Pent. Do you want to go through the prefixes real quick? Meth. Meth is the one. Meth, eth, pro, bute, pent, hex, hept, oct, non, and then deca. There's more after that, but I'd be surprised if you get anywhere close to that. And like I said, they're not going to come up with, I do not believe they will expect you to name something organic. But if you see something organic, to be comfortable with what it is. Do you have questions, Jackson?
Oh, no.
Oh, okay. So then we know it's got pent. What are hydroxides? Why are those on there? That tells me that this whole group here is an alcohol functional group. And so that means just it's got those extra hydroxyl groups on there. And so alcohols have their own special properties. They're very flammable. They tend to have very low melting points. And it's just kind of the way there. So for whatever that's worth, I don't think, like I said, I think what you would see on a question like this is they'd say, this is the compound, here's information about it. Here's a different compound, and here's information about it. And now you tell me which one makes more sense. They kind of compared two things in density last year, and you were able to look at different masses that they had, and you had to think about it that way.
So we need to know the characteristics of like alcohols.
No,
Carbeck's so fancy.
I do not think you need to know characteristics. I think they would give you characteristics, and then you'd be comfortable of saying what kinds of situations they'd give you.
We asked like intermolecular forces.
Yes, I was just going to say. So the best place to use these are intermolecular forces and give you molecules that you're totally unfamiliar with, and you trying to decide what kinds of intermolecular forces might be there. And when we did intermolecular forces, that's where you would do that chart where you'd compare like molecule A versus molecule B, and you'd have to think about like, is it ionic or covalent? And then if it's covalent, would it be polar or nonpolar? And if it's polar, would it be hydrogen forces or dipole-dipole or Lenz's dispersion also? And so when we get to the intermolecular forces, we'll come back to that. But those are the types of questions you're going to get organic questions about. And I truly do not think you'll name them. Okay, so this is an alcohol, but it also has double bonds in it. It has 2 double bonds in it. So you have to, instead of calling it an ane ending, you would call it an E-N-E ending, because A-N-E is single bonds, E-N-E is double bonds, Y-N-E means there are triple bonds. If you have double and triple, you just use both endings. You have, oh, I underlined my double bond, that's confusing. Okay, so we have 2 double bonds, and so you have to use the di in there. I did not leave myself very much room in there. And you also have to say where those are located. Drew kind of an obnoxious little one. So we have to name it 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. You can, but we really should look at the alcohol groups, because the alcohol groups are going to be the base of your parent chain. So wherever you're going to end with, that's kind of the key, that's the overall guiding everything. So since we've got an alcohol group here at 2 and an alcohol group at 2, could go either way. So then next we're going to look at our double bonds. And so we want to make sure that we get those the smallest as options, and it looks like we've got a 2 and a 2. So that means it doesn't matter. So we're going to call it 2, whatever, 2 and 4. Thank you. I've drawn all over this and I've lost myself. 2, 4 diene, but then once you've committed to something, you have to stick with it. I guess it doesn't matter because it's all the same. And so then my alcohol ending, do you guys remember? All OL. And I've got 2 again, so I have to call it a diol. And they're also on 2 and 4, just opposite 2 and 4. So pent 2,4, diene 2,4, diol. That's kind of what you would need to do. We've got carboxylic acids are the ones I have seen probably come up the most. And so they have this functional group. Acetate is the smallest carboxylic acid because C2H3O2. I guess it's not the smallest, but it's pretty small. I think one acid. And so it's going to have your carbon double bonded OH there on it. And that's why sometimes you'd see it written like that. Had your acetate ion. And then we turn it into acetic acid is when it's its carboxylic acid type atom. So we talked about alcohols and carboxylic acids. I think are the ones I've seen come up the most. So you're comfortable with those? Mm-hmm. Yeah, because they're both acids. So carboxylic acids are acids. Lots of times people forget that. So they always have this last hydrogen right here, and that hydrogen is really easy to donate. And if it donates that hydrogen, it's going to cause something to have a low pH, and it will be acidic, just like all of our other acids for whatever reason. Even though it's got acid in the name, people don't think of it like an acid, but it is. Yay.
And just like when they name like functional groups, if they have like an R, is that just like signifying carbons?
Right. That's exactly right. I would think they wouldn't just give you a functional group particular, give a compound and then tell you what the functional group is with it. And once again, I really think they'd give you the properties. Anything else?
One fluctuator that had like a unique molecule drawn out.
In your name, where it was carboxylic. And then alcohol.
Right.
And then ask the molecule.
I think
Are intermolecular forces used a lot on that?
yes. That's one of their biggest things. Intermolecular forces is a huge concept for the new version of the test. It was always a big deal in the past, but I've seen them focus on it a lot more now.
So we'll go over that next session.
We'll go over those when we do, yeah, that'd be next unit. Next time we'll probably talk about unit 3 and unit 4 maybe together. We'll kind of see how we go. Unit 3 was electrochem and unit 4 would be the atomic theory. That one we might need a whole individual review session for. So maybe we'll start it at the end of electrochem and then kind of move forward. So you guys have any other questions for me?
Well, they don't like empirical and molecular formula.
Empirical and molecular formula questions I saw on the older version a lot, but I haven't seen them as much on the newer ones. If you had any questions, you might have one. And a lot of times you can calculate it occasionally, but
Isn't that just like changing like C2H6 to like C1?
that would be to simplify a molecular formula to an empirical formula would be taking all your ratios and making it the simplest ratio. But you don't have a calculator on the multiple choice. So to have to calculate it, they either have to give you really simple math or it's a lot of time to spend to calculate. So they've taken almost all the math off of the multiple choice. And they've limited that a lot. And so on the FRQ, when you have the calculator, there's not a great lab to go with it, but you did do the hydrate lab, remember? That's the type of thing you would see. And I think we have a practice one if we haven't done it already, where you would see of like how you would do a empirical molecular formula and figure out what the compound is based on lab data. And we'll definitely do some of those in class when we're doing some review sessions. Anything else?
Can I check this book out?
Yes. Okay, bye computer people. If you watch this and you have any requests or complaints, let me know so I can do better next time. Thanks.